All right, welcome back. This is our last lesson, if you can believe that, in Unit 7 of AP Calculus. Unit 7, it's all about introducing you to the definite integral and the indefinite integral and the fundamental theorem of calculus that links the two together. Let's start with this practice problem, and we'll see how you do. Okay, so here's what you should have done. If f of 3 equals 5 and f prime is continuous, and the integral from 3 to 8 of f prime of x dx equals 20, find f of 8. Write an evaluated expression to show your reasoning. Well, you should have realized that f of 8 is equal to f of 3 plus the integral from 3 to 8 of f prime of x dx. In other words, it's the value at x equals 3 plus all the rates of change from 3 up to 8. So that would be 5 plus 20 is 25. Well, let's try this one. The integral from negative 1 to 4 of 3f of x plus 2 dx equals 28, and we need to find the integral of negative 1 to 4. So we'll split it up. All right, so I'll split it around this plus sign. I can do that, and I can actually pull the 3 out as well as a constant. And then we have the integral from negative 1 to 4 of 2. And I should distribute the dx to both of them. Well, we know that that is equal to 28. Now, we could actually do this using our integration now, but there's really no point. You know, it's just a horizontal line with a height of 2. And we're looking at the area from negative 1 to 4. Do you see that that makes a rectangle with a base of 5 and a height of 2? So that's just 10. So we have 3 times the integral from negative 1 to 4 of f of x dx plus 10 equals 28. So just doing a little algebra, I can say that, subtract off 10, make that 18, and divide by 3 is 6. So the integral from negative 1 to 4 of f of x dx, which is what we're supposed to find, is 6. All right. If f prime of x equals 3x squared plus 4x and f of 2 is 5, find f of 1. Give it a try. All right, so hopefully you realize that you can use the fundamental theorem of calculus, that f of 1 is equal to f of 2 plus the integral from 2 to 1, we're going backwards here, of f prime dx. So f of 2 is 5. And this integral becomes x cubed over 3 times 3 is just x cubed. Plus 4x squared over 2 is 2x squared. And we'll be doing that from 2 to 1. So this becomes 5 plus 1 plus 2 minus 2 cubed is 8. Remember to put when you plug a 2 in, start with parentheses. 8 plus another 8, right? 2 squared times 2. So we have 5 plus 1 is 6, plus 2 is 8. We have 8 minus 8 minus 8 is a negative 8. All right, let's take a look at practice 9.3. Read the problem and give it your best shot. Pause the video. All right, let's see how we did. After a soccer game, fans leave the stadium at a rate of r of t people per minute, where t is the number of minutes since the end of the game. Selected values of r of t are shown in the table. You can see that r of t, the rate, is in peoples per minute, and t is in minutes. We're going to use a right Riemann sum with 3 subintervals to estimate the number of people who leave the stadium during the first 30 minutes after the end of the game. So the number of people that leave the stadium is simply the adding up of all the rates of people leaving for those first 30 minutes. So we're going to say that this is the number of people that leave the stadium is the integral from 0 to 30 of r of t dt. That's going to add up all those rates. We're going to use let's see here, 3 subintervals and a right Riemann sum. Okay, so 1, 2, 3 subintervals. Okay, this rectangle is a 10 and a height of 300. This rectangle here is a width of 10 again. Ooh, I almost put 20. 10, again, with a height of 100. And this one here is a width of 10 with a height of 50. So keep in mind the rate of people leaving, if we were to graph it 0 to 200, then at 10 we're at 300, and then at 20 we're back at 100, and then here at 50. So it's some sort of curve, and we're using a right Riemann sum. So we're going to be adding up all of these rectangles here to get an estimate of the total number of people that left. Also note that this is people per minute, and this is minute. When you multiply the change in minutes times the number of people per minute times minutes is just people. Integrating takes away a per, typically. So this is going to be all right, well, so let's add these up. Well, this is 3,000 plus 1,000 plus 500. So 4,500 people is what it looks like. 4,500 people have left the game. Suppose that at the end of the game, there were actually 8,200 fans in the stadium. We're just going to write an integral expression for the number of people still in the stadium. So the number of people still in the stadium is the number of people that we have when the problem starts, minus all the people that leave, which is the integral from 0 to 30 of r of t dt. Now we can estimate that value by simply using the value that we calculated in part A, 4,500. And I think that's, what is that, 3,700, I think. So that's how many people are still left in the stadium. We should label the units, shouldn't we? People. All right, let's go to example 9.2. We're going to evaluate the integral from -1 to 4. So, let's see. From 3x minus 1, where x is less than or equal to 2, and x squared plus 1 when x is greater than 2. So what happens at x equals 2? Well, at x equals 2, the top branch is 5, and the bottom branch is also 5. Or to be more precise, we could say the limit as x approaches 2 from the left and from the right is the same, so the limit exists. The function value exists, it's 5, and they're the same, so we must be continuous there. So we can simply evaluate this by breaking it apart and using the integral from -1 to 2 of f of x dx plus the integral from 2 to 4 of f of x dx. All right, well, this is going to be, let's integrate from -1 to 2. We need to be using the top branch because we're less than or equal to 2. So that'll be 3x squared over 2 minus x, and we'll be doing that one from -1 to 2, plus we got the integral from 2 to 4. We'll be using the bottom branch, which is x cubed over 3 plus x. And that's going to be from 2 to 4. Now, you might be a little confused. Hey, how can I include 2 here when this is only for x greater than 2? But remember, the integral from 2 to 2 is 0. So this is really just the boundary of it. It doesn't, we're not overlapping any. If anything, we're overlapping with a difference of 0 between the two. So they were just lining them up. It's a perfectly legit way to do this. Plugging in, this is going to give you 12 over 2 is 6, minus 2 is 4. And you should write it all out, not try and do it in your head like I am, but I'm trying to save some space here. That's going to be 3 over 2 plus 1, which is 5 over 2. And then this one here is going to be 64 over 3. Plus 2. And so, oh, that's too ugly. I don't want to do this. We'd have to get them all in terms of 6. So I'm just going to leave the answer like that. All right. In the previous example, f was a continuous function. So we know that the definite integral can be evaluated. We talked about that. We talked about our fundamental theorem of calculus. We can show that if it's continuous on that interval from a to b, then we know that the interval from a to b, I'll use f of x dx, is equal to the antiderivative, so use a capital letter F, valued at b minus the antiderivative at a. That's if it's continuous. Well, it turns out this theorem can and is strengthened a little bit to handle the case of when it's not necessarily continuous, but they call it like Riemann continuous. And I don't want to go into that. I just, and it's not necessary, but just I want you to be aware that it is possible to still have an integral in some cases when they're not continuous. So let's take a look. F of x. 4x when x is less than or equal to 1, 3x squared plus 1 when x is greater than 1. If you plug in 1 for x to take the limit from the left on the top, you would get 4. But on the bottom, you would also get 4. I thought I was going to show you when you can't. Yeah, well, let's just change that problem a little bit. I guess and let's do this. So here's one where they're not continuous. So plug in 1, you get 4. Plug in 1, you get 5, right? And it turns out that, if you graph this, what we have is this situation where there you got a straight line up until x equals 1, and then all of a sudden we're going to switch up here like that. But the area from -1 to 2 is going to be all of this area here. And then it's going to be all of this area here. Well, that's still something that we can find the area of. So as long as there's like just that one little break, we can still do it. So let's go ahead and find the integral here. We'll have to split it up. I'm trying to change colors. And it's split it up from -1 to 1, in which case we'll use 4x dx. And then we're going to add 1 to 2. In this case, we'll use 3x squared plus 2 dx. Okay, so this ends up becoming 4x squared over 2, which is 2x squared, from -1 to 1. And this ends up becoming x cubed plus 2x from 1 to 2. And from -1 to 1, this would be, let's see here, this would be 2, and then plus 2, actually, 2 minus 2, because that -1 squared is a positive 1, but remember, we got to subtract the second number, right? Plus, and then this would be 8 plus 4 is 12, minus 1 plus 2 is 3. So we get 9. So in that case, we actually can do it. You don't really see this on the AP exam because, it's just a little bit kind of controversial, but you really can calculate the integral in that situation. However, when we have an asymptote in our interval, we absolutely cannot do it. So this function here, x squared plus x to the -2, if you try and plug in 0, you would get a number going to infinity from the left and right. So we end up with, let's see, I want to say this graph looks something, something like this. And this goes up forever. We cannot find what that area would be, because the higher up you go, the closer you get to 0, the higher up you go, the more area you have. So we're going to say that no, we're not going to do that one. All right. Now that we are more familiar with definite integrals, let's revisit our formal definitions and look at some interesting practice problems. All right, the definition of a Riemann sum. If a function f over the interval from a to b is partitioned into n subintervals using any n plus 1 points. Remember, if we want to have 10 subintervals, we got to have a point at the beginning and a point at the end. And then we got to have, 9 points in the middle. That makes 11. So it takes n plus 1 points. I'm going to call them x sub 0, x sub 1, all the way to x sub n. We'll let delta x sub k equal the width of the kth interval. So that delta x sub k is delta x sub k minus delta x sub k minus 1. And we'll let c sub k be some randomly chosen x value in the kth interval. Then we know that the Riemann sum is f of that randomly chosen point. It could be a left endpoint, right endpoint, midpoint, or just anything, times the width of that interval, which we're calling delta x sub 1, plus f of the c from interval 2 times the delta x of interval 2, plus all the way down to f of c of the nth interval times the delta x of the nth interval. That is a Riemann sum of n intervals. This can be written in sigma notation using k as a subscript, k going from 1 to n, and we add them all up. If the number of subintervals n approaches infinity, then the value delta x for the kth interval must approach 0. Likewise, if delta x is the largest interval in the n subintervals and it approaches a 0, therefore what we're saying is if the largest delta x goes to 0, then we've got to have an infinite number of them. That means n goes to infinity. So a limit as n goes to infinity or a limit as delta x goes to 0 are both two ways to express the definite integral. That gives us these two formulas here. So remember, a definite integral really is a limit. So let's take a look at this question. If n is a positive integer, express the following as a definite integral. Wow, look at that. How are we supposed to figure that out? Well, and they could even ask us to maybe evaluate this, to have to add all those things up. Well, that would be really difficult, but I have a hint for us. What we're going to do is remember that this 1 over n is simply our dx value, okay? So we're going to, that 1 over n is that change in our interval. So we're going to evaluate the limit as n goes to infinity of the first terms inside the function and the last term. And if I do that, that should tell me the a and b. Since f of a has got to be this thing and f of b this last thing. So let's take a look. The limit as n goes to infinity of 5 plus 1 over n. Well, if I plug in infinity, 1 over infinity is 0, and 5 plus 0 is 5. The limit as n goes to infinity of 5 plus 3n over n, well, in that case, the n's reduce out, and I just get 5 plus 3 is 8. So what's happening is we're just squaring every number from 5 to 8 and adding them up. Well, we know how to do that. So that is the integral from 5 to 8 of, what am I doing? Squaring. X squared as x goes from 5 to 8 dx. I said there could be multiple correct answers because someone else might come along and say, well, isn't that really the limit of 1 over n? Doesn't this 1 over n start at 0 and 3 over n goes to 3 of x or 5 plus x? Aren't they really adding 5 to x? But that's the same thing. You could do a u substitution and confirm that these are, in fact, the exact same thing when you change the bounds. All right, let's try this one. If n is a positive integer, then the limit as n goes to infinity of all of that is equal to what? Well, we know that this 1 over n business, and remember, this is just a dx here, right? That's just a dx. So this is just our dx, so I don't need to worry about that, okay? I do need to add up all of these things. Well, let's take the limit. The limit as n goes to infinity of this term, well, that's 0. And in this term, that's 3 again, right? So this must be the integral from 0 to 3 of x squared dx. And there we go. Look at these kind of sucker answers. They expect you to think that 1 over is in it. No, no, no. Really narrows things down, doesn't it? Let's try this one. The limit as n goes to infinity of 1 over n times, okay, well, what is 1 over n's limit? When you take the limit as n goes to infinity, that's 0. What about that? That's 1. So the integral must be the integral from 0 to 1 of the square root of x dx, making the answer B. All right, let's try 9.5. I want you to try this clever little problem yourself. The closed interval from a to b is partitioned to n equal subintervals, so we know we're thinking about a definite integral here, each of with delta x, but the numbers are a equals that, where x is all that stuff. So that's just coming right from the definition of definite integral. What is the limit as n goes to infinity of the sum from I equals 1 to n of x of I times delta x? Try and figure that out. Make a definite integral first. All right, let's see how you did. So we were told that we're going from A to B. So that made that part easy for us, right? The function is the square root of x, and this delta x must be going to infinitesimally small dx. So we're really just evaluating this, which is equal to the integral from a to b of x to the 1/2 dx, which becomes x to the 3/2 times 2/3 from a to b. All right, I can factor out a 2/3 and call this b to the 3/2 minus a to the 3/2 when I use the fundamental theorem, making the answer C. Pretty cool, huh? All right, I think this is our last problem in the unit. I got the graph of W prime shown here. That is a semicircle and a couple line segments. I would like for you, please, to answer A, B, and C. Okay, let's see how we did. If W of -1 is equal to 4, find W of 3. Okay, no problem. W of 3 is equal to W of -1 plus the integral from -1 to 3 of W prime, which is shown in the graph, of x dx. Well, this is a semicircle with a radius of 2, so it'll be pi r squared over 2. W -1 is 4, so pi r squared, where r is 2, pi 2 squared is 4 pi, over 2 is 2 pi. Classify the value we found in part A as a relative min or relative max. Well, this value here, oh, you know what? We only found W of 1. Oh my goodness, I haven't finished. I'm sorry. Let's say, well, that value there is not a relative on anything, but over here, definitely. Because we got to go all the way to 3. So I need to keep going. That 2 pi, that's the area of this semicircle, because the area would be 4 pi for the whole circle. And then this is a triangle with a height of 2 and a base of 2. So 4 divided by 2 is 2. Okay. So that's 6 plus 2 pi. Well, what is it? Well, it's got to be a relative maximum because W prime changes from positive to negative. And take a look. After 3, what would happen to W? If we got to find W of 4, would W4 be less than W3? Well, of course, because we have to add all these negative integral to it, wouldn't he? All right. So let's find W of -3. What would that be? Oh, you know what? Boy, I tell you, I keep messing this up. This should not be 2 pi. This was actually 1/4 of a circle. Yikes. 1/4 of a circle. So it really should have been from here over. Sorry about that. So that should be just a single pi. All right, well, I'm struggling on this one. Sorry. All right, W of -3 would be W of -1 plus the integral from -1 to -3 of W prime of x dx. The integral from -1 to 3, that's just pi, because the whole circle is 4 pi. But that's 1/4 of it, so just pi. But we're moving backwards. We're going in this direction, so it's going to be a negative pi. And W of -1 is 4, so it's 4 minus pi. All right, that is the end of the unit, and I'll see you in the next one.